Hello and welcome to this video workshop all about chemical bonding and atomic orbitals. So this series of video workshops is designed to help the transition of foundation year and first year students into chemistry focused modules who maybe don't have a strong previous background in chemistry. You'll need around 20 minutes to complete this video workshop. There are a number of quick practice questions throughout. At these points you should pause the workshop and work through the questions at your own pace. To get the most out of this session, you'll need a periodic table and something to write or draw with. A periodic table can be downloaded from the main SharePoint page from which you access these videos. So what are we going to try and learn today? Recall why elements bond to achieve a full outer electron shell. We're going to look at using your periodic table to work out how many outer shell electrons the many different elements have. By the end of this session, you'll be able to describe and understand the differences between ionic and covalent bonds and bonding. We're going to look at two different types of electron orbital and understand their differences, and in particular their different shapes. And hopefully by the end of the session you'll have the ability to construct what we call an atomic orbital energy level diagram for some of the simple elements. Right, why is this important first of all? Well, thinking about it, if different atoms and molecules did not react, join together and split apart, there would be no chemistry, and indeed there would be no life as we know it. The human body and all of the processes that go on inside it rely on chemical reactions. In other words, things bonding and things splitting apart to work. So it's a very, very fundamental concept to not only chemistry and chemical sciences, but biochemistry and biology as well. There are many different types of bonding possible between elements, and you need to be familiar with all of them and be able to describe all of them in simple terms. In one respect, all types of chemical bonding are alike. The controlling force is that atoms want, in quotation marks, to achieve stability. So they want to sit in the lowest possible energy configuration. Very much like a lazy person, they don't like doing things that raises their energy level. We should start with a little reminder of the structure of atoms. Atoms consist of a nucleus made up of positively charged protons and uncharged neutrons. These make up the huge bulk of the weight of the atom. Around this we have negatively charged electrons that whiz around the nucleus very, very, very fast. One of the key ways in which atoms like, again in quotation marks, to achieve stability is by gaining a full outer shell of electrons. When they do this, they attain what is called the noble gas configuration. You might remember from previous education that group 18 of the periodic table, highlighted on the right here, are the noble gases, and they are very, very unreactive. They are unreactive because they all have full outer electron shells. Now, as we go down the periods, or rows in plain English, of the periodic table, the number of electron shells that an atom possesses increases. You can think of electron shells as layers of electron density, moving gradually further and further away from the nucleus of the atom. In the first period, atoms only have one electron shell, and it can hold a maximum of 2 electrons. In the second period, the atoms have 2 electron shells, and this time the outermost shell can hold 8 electrons. In the third period, the atoms have 3 electron shells, and the outermost shell can also hold 8 electrons. We won't go any further than that today in terms of complexity. There are a few ways in which atoms seek to achieve this full outer electron shell. They can take electrons from another atom, they can lose electrons to another atom, or they can share electrons with another atom. The first two ways result in what we call ionic bonding. And a very good and simple example of this is sodium chloride, which, as you might know, is just common table salt. It's made up of sodium and chlorine elements. Sodium atoms have just one electron in their outer shell, whereas chlorine atoms have 7, so their outermost electron shell is nearly complete. Here's a very easy way to work out how many electrons each group has in its outer shell using your periodic table. So starting on the left-hand side, group 1 has 1 outer shell electron, group 2 has 2. We then get this big and somewhat confusing block in the middle, including things like transition metals, lanthanoids and actinoids. Let's not worry about them for now. They come much later in your chemistry education. When we get all the way over to group 13, the kind of nice pattern that we've established continues. Group 13 elements have 3 outer electron shells, group 14 have 4, and it goes on until group 18. Now remember what I said, atoms are lazy and want to find the lowest energy pathway towards doing anything. Thinking about it rationally, it's much easier for a sodium atom to give up 1 electron than to gain 7. On the other hand, for a chlorine atom, it's much easier to gain 1 electron than lose 7 to attain that full outer electron shell. So in a sodium chloride salt crystal, the sodium atoms have all given up 1 electron and the chlorine atoms have all gained 1 electron. So everyone in the lattice has a full outer electron shell and everyone is happy. In doing so, the atoms, of course, cease to become atoms. They turn into ions. So they no longer have equal numbers of protons and electrons. Remember, each proton carries a charge of +1 and each electron carries a charge of -1. So the sodiums in sodium chloride are all positively charged and the chlorines, or chlorides rather, are negatively charged. This is why it's called ionic bonding. You turn atoms into ions. Now when we look at elements like nitrogen and carbon with 3 and 4 outer shell electrons respectively, you can imagine that they don't actually like to ionic bond very much because it takes a lot of energy either to lose or gain a large number of electrons to complete the outermost shell. So what they do instead is they share electrons with other atoms. We can illustrate this with the molecule methane. So the chemical formula for this is CH4. So we have a carbon atom surrounded by 4 hydrogens. In the diagram, the electrons belonging to the carbon are shown with black crosses. Those belonging to the hydrogens are shown with red dots. Now remember, everybody wants that full electron shell. So if the carbon shares 1 of its 4 outer shell electrons with each hydrogen, and each hydrogen in turn shares its 1 electron with the carbon, you can see that the carbon gets 8 electrons in total, completing its shell, and each hydrogen gets 2 electrons, completing their outer shells. So again, everybody is happy and stable in this configuration. These bonds are called covalent bonds. So covalent means shared electrons. And covalent bonds, and in particular the fact that carbons form 4 covalent bonds, commonly with neighbouring atoms, are the main reason why biomolecules like peptides, proteins, nucleic acids look the way they do, and the main reason why drug molecules look the way they do. In organic chemistry drawings, we usually represent covalent bonds with sticks, just like we see on the right here. As a little exercise, why not have a go at drawing out the simple structures of these 2 molecules, showing with each example how the electrons are shared using the rules that we've just explained and applied for methane. It's easiest if you use dots for one set of electrons, so for the hydrogens, and crosses for the electrons from the other atom. So pause the video now and have a go at that exercise and see how you do. So here are the solutions to that quick exercise. So have a look at what we've got on the screen here and check that that corresponds to what you drew, what you came up with. If it doesn't match, take a moment to digest this slide and understand where you went wrong. It's usually just a simple case of people forgetting to apply the basic rules, which state that in covalent bonding systems, all of the atoms involved need to have that full outer electron shell. For the hydrogens, they're going to have 2 electrons. For the huge majority of other atoms that you're going to be dealing with, they need 8 electrons in their outer shell. Let's move on to double covalent bonds. Now, as you might know, some hydrocarbons have double covalent bonds in them. All this means is that between the 2 bonding atoms, there are 2 pairs of shared electrons. So thinking about the simplest example, ethane, 2 carbons and 4 hydrogens, for example. Each carbon atom is bonded to the other carbon and to 2 hydrogens. It shares 1 pair of electrons with each hydrogen and 2 pairs with the other carbon, making the double bond. Notice how the carbons still have 4 covalent bonds coming off them in total. 2 singles and 1 double. In organic chemistry drawing, we represent the double bond with 2 lines close together as shown. Right, now, having told you all that, everything we've just learned is a simplification. So, of course, the 2 electrons in a covalent bond do not just sit still nicely between the 2 parent atoms like I've drawn on the left. Electrons are constantly moving very, very fast, in fact. So to understand bonding at a higher level, a university level, in fact, we need to introduce the concept of electron orbitals. What does this mean? Well, you can think of an electron orbital as the path that an electron takes around the nucleus of its atom, the atom that it belongs to, in 3-dimensional space. Orbitals take a number of different 3-dimensional shapes. So considering the carbon atoms that we've just drawn, the outer shell electrons, they don't just run around in a circle around the nucleus as I've drawn. It's more complicated. And as we go down the periodic table to some of the heavier and more complex atoms, the possible orbital shapes grow increasingly more complicated as well, and harder to remember. But let's start very simple. So in the first period, we only have 1 electron shell to worry about. It is spherical in shape and it can hold a maximum of 2 electrons. So hydrogen has 1 electron, helium has 2 and is full. We call this the 1s subshell because it's the first shell away from the nucleus, the closest one to the nucleus, and you can remember it by thinking S for sphere, or even S for circle if you prefer, although that's not technically right. Subshells are various different 3D shapes and they can hold different numbers of electron orbitals. Again, the orbital is just a pathway that an electron takes around the nucleus in 3D space. In books and videos, you'll sometimes see the shapes of the subshells represented like as we see on the left hand side to show their 3-dimensional nature. However, you'll also see the shapes just drawn very crudely in 2 dimensions rather, like I've done on the right. And so that's our first period done. So in our second period, and if you want to follow along on your own periodic table, this is the one that starts with a lithium on the far left. We have up to 8 outer shell electrons to worry about. So in the second period elements, the 1s subshell is always full with 2 electrons. In the second electron shell, there are 2 subshells. We start with the 2s subshell. This is very much like the 1s as it's spherical in shape. It's just larger as it's further away from the nucleus. and it too holds 2 electron orbitals. The number 2, as you might imagine, simply refers to the second electron shell away from the nucleus. We then also have the 2p subshell, and within this are 3 different orbital types. They have a different shape. They look like this, as we see on the right. Rather like a peanut, in fact. If it makes it easier to remember, think P for peanut. There's one of these for each of the 3 dimensions. So if we draw a set of 3D axes, Cartesian coordinates is the posh name for this, and imagine our atomic nucleus is in the centre here. One 2p subshell points this way along the x-axis, one points along the y-axis, and one along the z-axis. When you look at these coordinates, you have to try and imagine that the z-axis is coming out of the screen towards you and simultaneously going away from you. So it's like this. We represent that with a wedge line going forward and a dashed line going backwards. So we call each subshell 2px, 2py and 2pz respectively. And that's our second period done. In our third period, the rules are very similar to the second period with respect to the 3s and 3p subshells. In the third electron shell, there is actually a third type of subshell. It's called the 3d subshell. But confusingly, it doesn't actually start getting filled with electrons and isn't involved in bonding until we get to the fourth period elements. The orbital shapes are rather more complex, and in fact you might never have to learn about them, so we won't discuss it any further now. Here's a key point to remember. In a given electron shell, p orbitals are higher in energy than s orbitals. Imagine running around in a circle versus running in a figure of 8 pattern. You'd use more energy getting back to the same starting point if you were running the figure of 8. It's the same for the electrons. They're doing more work, so they're higher energy. We can represent the energy levels for the different subshells and orbitals in a very simple diagram. So on our y-axis going upwards is energy level, and each of these little horizontal lines represents an orbital type, and each one holds a maximum of 2 electrons. So here's 1s, then 2s, and then the 3 2p orbitals, all at the same energy. You can show the electron configuration of any element by drawing a diagram like this. There are only 2 things that you have to remember. The first is that the lower energy shells and subshells get filled with electrons first. And the second is, for orbitals of the same energy level, each orbital gets filled with 1 electron first before any are filled with 2 electrons. As always in chemistry, there are some exceptions to this, but at this level we don't need to start worrying about them. The second point, we can almost call it the bus seat rule. If you go onto a bus or a train, it will usually have 2 sets of 2 seats close together. Now in the UK, unless you're a bit of a weirdo, you won't go and sit next to a stranger if you can help it. You'll find an empty set of 2 seats and sit there. The sets of seats don't become doubly occupied until the bus starts getting busy. So if that helps you to remember the rules, then you can bear that in mind. It helped me when I was an undergraduate. Let's go through this exercise with focusing on a single carbon atom. We have 6 electrons to deal with. Remember that you find the number of electrons in an element from its atomic number in the periodic table. The atomic number is always the same as the number of electrons. So the first 2 go into the 1s subshell. We draw the electrons like this, with 1 half arrow pointing up and 1 pointing down. We don't need to go into the reasons for doing that at the moment. So that's 2 electrons accounted for. And then the second 2 go into the 2s subshell, because that's the next lowest energy level. And then we've got 2 electrons remaining, so 1 each goes into 2 of the 2p subshells. Remember, they're all singly filled before they get doubly filled. You don't need to worry about whether you put them in the px, the py, or the pz orbital. It's completely arbitrary. And this very simple diagram represents the atomic orbitals, or the electron configuration of a carbon atom. Right, over to you again now. Have a go at drawing out equivalent diagrams to the one I've just done for the atomic orbitals of these elements. Just follow the rules as we did with carbon. So pause the video here, and then when you're ready to check what you've done against the correct solutions, carry on. So here are the atomic orbital energy levels for oxygen and phosphorus. Again, check these carefully against what you wrote down or what you drew. And if you've gone wrong, understand how. It's simply a case of following the 2 rules that I've already outlined. And that takes us to the end of the learning materials on atomic bonding and atomic orbitals. So just a quick recap of the learning objectives there that we've hopefully comprehensively covered for you. I hope you've enjoyed the video and the learning. Remember, there are plenty more practice problems for you to have a go at to make sure that you've understood the learning. If you're watching this video when it was first released, you can come along to the workshop session that we have planned later in semester 1 and get extra advice from one of the instructors if necessary. If you're watching this after the workshops are finished, in revision period perhaps, you can access copies of the practice questions and answers using the links provided below the video. Thank you for watching.